this lesson, we are going to solve absolute value equations algebraically. We're going to use the same equations that we solved graphically in the notes. We'll start with example 1. When we solved example 1, the equation was the absolute value of x plus 2 is equal to 4. Solving this graphically, we got two solutions, x equals -6 and x equals +2. The reason we got two solutions is because if what's inside the absolute value was positive, it would have to equal a +4. And if what's inside the absolute value were negative, it would have to equal a -4. If we solved each of these equations algebraically by getting the x by itself, we would wind up with two different answers. X equals 2, which was a graphic solution, and x equals -6, which was also a graphic solution. Let's turn the page and break down the steps of how we could do this for a more complicated problem. For try number 2, our equation had the absolute value of x minus 1, then a -4 equals -1. The first step to solve this equation algebraically is going to be to isolate the absolute value. What that means is we need to get the absolute value by itself. In this equation, we would add 4 to both sides of the equation to get the absolute value symbol by itself. For the next step, we're going to break our equation into two parts. In the first part, we leave the equation the same, we just drop the absolute value equation part. For the second part, we also drop the absolute value bars, but we take the opposite of the right side. So our 3 on the right becomes a -3. Next, we're going to solve each of these equations separately. On the left equation, I add 1 to both sides to get x equals 4. On the right equation, I add 1 to both sides to get x equals -2. Last, we're going to check each of these solutions by plugging it back into the original equation. If I plug 4 into the original equation, I have 4 minus 1, which is 3, the absolute value of 3, which is 3, and 3 minus 4, which is -1. So -1 equals -1, and x equals 4 is a true solution. If I plug x equals -2 into the original equation, I have -2 minus 1, which is the absolute value of -3. That's then -4, which is 3 minus 4, which is -1, which equals -1. So x equals -2 is also a solution. If I didn't want to plug back to the original equation to graph, I could also look back at my original graph over here on the left and see that graphically I had two solutions because in both cases my graph crossed twice at x equals -2 and at x equals 4. Turn the page to example 2 and pause the video while you try example 2 on your own. In this equation, to isolate the absolute value, I divided both sides by 2. I broke the equation into two separate parts, one where the absolute value was equal to +5, and a second where the absolute value was equal to -5. I solved each equation and got 4 and -6. Then I checked by plugging x equals 4 into the equation, which worked out, and x equals -6 into the equation, which worked out. Turn the page and pause the video while you attempt try number 5 algebraically. For this equation, to isolate, I divide both sides by 5, giving me the equation, the absolute value of x plus 1 equals -2. Hopefully at this point I would notice the absolute value can never equal a -2, so this equation is not going to have a solution. If I didn't notice, I would break the equation into two parts. The first one, where everything stays the same, yields x equals -3 as my solution. The second equation, where I take the opposite of the right-hand side, gave me x equals 1 as a solution. The problem with both of these solutions is that when I go to check them, I plug into my original equation, work myself down, and I wind up with 10 equals -10 as a final answer. That equation is not true for either solution, so both of these are going to get crossed out, and I need to write no solution as my answer. Again, I can put that in words, or I can do the curly brackets with nothing inside them. These are called extraneous solutions. Extraneous solutions are solutions we get when we solve algebraically that don't really work out. Again, the easiest way to see this is by looking at the graph, which we did in the original notes, and the graphs never touched. Going down the page, let's look at example 5. Example 5 is 2 absolute value of x plus 3 is equal to 4x plus 4. Pause the video while you attempt to solve example 5 algebraically. I divide both sides by 2 to get the absolute value by itself. When I break my equation into two parts, my first part leaves everything the same and drops the symbol. In the second equation, when I negate the right side, I'm going to have to distribute and make this a -2x minus 2. Now I'll solve the rest algebraically. I get x by itself in each of these equations and wind up with x equals 1 and x equals -5/3. I still have to go back and check to see if they work in the original equation. When I plug back into the original problem, x equals 1 works out because we wind up with 8 equals 8. When I plug x equals -5/3 into the original equation, not only do I have some nasty fractions, but I wind up with a statement that's not true. So x equals -5/3 is an extraneous solution. This problem only has one solution. If we looked at the graph, that solution was nice and obvious because, as we saw before, our graphs only crossed one time, and the x value where they crossed was x equals 1. Solving algebraically is a great way to solve absolute value equations, but remember, it's really important we go back and check our solutions. Sometimes we'll have one solution, which is shown by the graphs crossing one time, or one of the solutions working when we plug in. Sometimes we'll have two solutions because graphs will cross twice, or both solutions will work when we plug them back in. And other times we'll have no solution because the graphs will never cross and we won't get any solutions that work when we plug them back in.